Hello, my name is Luis Murillo. I'm gonna talk about deep learning for radio frequency systems. Definition: deep learning within radio frequency shows promise for dealing with a congested spectrum by enhancing reliability and simplifying the task of building wireless systems. AI manifestations like machine learning and deep learning can invoke data analysis to train radio signal types in a few hours. For instance, a trained deep neural network takes a few milliseconds to perform signal detection and classification as compared to traditional methodologies based on iterative and algorithmic signal search and signal detection and classification. Now I present a video about deep learning for signals.
Deep learning continues to gain popularity in signal processing with applications such as voice assistants, digital health, and radar and wireless communications. With MATLAB, you can easily develop deep learning models and build real-world smart signal processing systems. Let's take a closer look at the 4 steps involved. The first step in building a deep learning model is to access and manage your data. Using MATLAB, you can acquire signals from a variety of hardware devices. You can also generate synthetic data via simulation or use data augmentation techniques if you don't have enough data to begin with. MATLAB simplifies the process of accessing and working with signal data that is either too large to fit in memory or if you have large collections of signal data. Once the data is collected and ready, it's now time to interpret the signal data and label it. You can quickly visualize and analyze your signals using the Signal Analyzer app as a starting point. You can label signals with attributes, regions, and points of interest, and use domain-specific tools to label audio signals to prepare your data for training. There are 2 main approaches for performing deep learning on signals. The first approach involves converting signals into time-frequency representations and training custom convolutional neural networks to extract patterns directly from these representations. A time-frequency representation describes how spectral components in signals evolve as a function of time. This approach enhances the patterns that may not be visible in the original signal. There are a variety of techniques for generating time-frequency representations from signals and saving it as images, including spectrograms, continuous wavelet transforms or scalograms, and constant Q transforms. The second approach involves feeding signals directly into deep networks, such as LSTM networks. To make the deep network learn the patterns more quickly, you may need to reduce the signal dimensionality and variability. To do this, you have 2 options in MATLAB. You can manually identify and extract features from signals, or you can automatically extract features using invariant scattering convolutional networks, which provide low variance representations without losing critical information. Once you select the right approach for your signals, the next step is to train the deep networks, which can be computationally intensive and can take anywhere from hours to days. To help speed this up, MATLAB supports training on single or multiple NVIDIA GPUs on local machines or cloud-based systems. You can also visualize the training process to get a sense of the progress long before it finishes. Finally, you can automatically generate optimized CUDA code for your signal pre-processing algorithms and deep networks to perform inference on embedded GPUs. To learn more about our deep learning capabilities, check out mathworks.com. We have a large collection of examples to help you get started.
Application of deep learning in radio frequency systems. I might image and video recognition. Have multiple channels, RGB, X, Y, spatial dependence, temporal dependence video. For audio and language, have single channel, frequency, phase, amplitude, temporal dependence. For systems and signals, have multiple channel, frequency, phase, amplitude, temporal dependence, complex data, IQ, large bandwidth, and human in general. Now I present a video about Deep Wave digital product. Pros and cons. The pros: some hardware have adaptable architecture, high real-time bandwidth, software programmable, high power efficiency, low latency. The cons: in some hardware have limited real-time bandwidth, higher latency, not well integrated into radio frequency, limited reprogrammable. Use applied in Ecuador. In Ecuador, the use of radio frequency systems is generally used for communication, implementation of deep learning facilitate a better awareness of the operational environment and promise to offer end-to-end learning for creating an optimal radio system. Case in point, a traditional model can jointly learn an encoder and decoder for a radio transmitter and receiver while encompassing radio frequency components, antennas, and data converters. Now I present a video about an application of capturing a human figure through a wall using radio frequency signals.
This video describes a device that can capture the human figure through walls using RF signals. We place our device behind the wall, and it can see the silhouette of a person who walks in an adjacent room. The device works correctly even if the room is completely closed. For example, if a person stands behind the wall, the device's output looks like this. In particular, the output on the right shows the background in navy blue and the various human body parts in red, orange, and yellow. Here, we can see the person's head, chest, arms, and feet. How does this work? The device operates by transmitting wireless signals that traverse the wall, reflect off the human body, and come back. At every point in time, only a subset of human body parts reflect the signal back to the device. Here, we show the output of the device as the person walks. At different points in time, different parts of the human body reflect the signal, and the device captures multiple snapshots at various points in time. It then combines these snapshots through a reconstruction algorithm that allows the device to recover the human silhouette through the wall. Here, we can see the person's head, chest, arms, and feet. The device can distinguish between different people behind the wall. So for example, over here, we ask two different people to stand behind the wall, and this is the output of our device. By training on different subjects, we can use a classifier to distinguish between them. The device can also distinguish between certain human postures. If the person stands straight, the output looks like this. While when someone stands in other postures, the device's output reflects his postures. The device can also track human limbs from behind the wall. Here, we show a scenario where a person draws a shape in the air, and we show the output of our device to the right. The device can trace the person's hand with high accuracy. We compare the device's output to that of a Kinect placed directly in front of the person and show the Kinect's output in red. In comparison to Kinect, our median error is around 2 centimeters. For more information on how the device works, check out our project webpage.
Conclusion. In conclusion, the implementation of technologies like deep learning promise to address the signal complexity of radiofrequency systems by employing powerful machine learning algorithms and significantly improving radiofrequency parameters such as channel bandwidth, antenna sensitivity, and spectrum monitoring. Thank you.